Even samen lopen en samen gaan. Ja, ontzettend.
Are these papers from the last class?
Oh, I think they're blank paper in previous class. I was gonna say, like, I'm pretty impressed they've done recruiting here. I know Joe Fitson. Joe Fitson. Okay, so hi everyone. Let's get started. So, today we're going to there's two parts. The first part is we're going to finish up this unit on tomography. And then we're going to get into this Q&A session, which I'm really excited about. I saw the stuff that you all submitted. And I think the questions you asked are really fantastic. And I think that it'll be a lot of fun to discuss them. But before that, we have to finish up our section on tomography. So let's do that. Some basic administrative stuff. Problem set 2 is going to be out this weekend. The due date is going to be March 7th. Also, the project guidelines and some more information about your research projects are also going to be posted this weekend. And the proposal for your project is also due on the same day. And I'm putting them on the same day because I want you guys to look for project partners. And you can also work together on the problem set and so on and get all that done by March 7th. And in the meantime, I'm more than happy to discuss with you any questions you have about the project you want to bounce ideas off of me, or you want pointers to the literature or pointers to papers, I'm more than happy to provide that. So that's all the administrative stuff. Any questions about that? Okay. So let's finish up. We didn't quite finish this last time, but we started talking about a tomography algorithm that only works for pure states. And it's going to use all this machinery that we've developed about Haar randomness and the symmetric subspace. And the reason we're considering it is because its sample complexity, the number of copies of the pure state you need in order to get a good estimate of your state, is linear in the dimension of the state. And divided by epsilon, where epsilon is how close you want your estimate to be to the unknown state. And this is really nice because this comes very close to the lower bound that we proved a few lectures ago, right? It's a difference between O of D and D over log D. So there's just a tiny gap, which is still open. So if someone wants an open problem, closing this gap is that open problem. So let's see how it works. And it's going to make use of this thing called a continuous POVM, right? It's this thing we covered last time. It's a type of measurement where the set of measurement outcomes is a continuous set. The algorithm gets as input k copies of the unknown state at psi. We're assuming it's a pure state. And we're going to perform the following POVM. So the POVM is going to be an infinite set of operators. Each of these operators are positive semi-definite. There's one operator for every single pure state in D-dimensional space. Right, so it's this infinite family. You can think of, remember a picture of the unit sphere, CD, S of CD. For every point on this unit sphere, there's going to be a different operator. And that's our continuous POVM. This operator is defined in the following way. It's going to be k tensor copies of this state theta, and we're going to weight it by this binomial coefficient. Right. We should recognize this as this is the dimension of the symmetric subspace. And last time we verified that this was indeed a continuous POVM. If you integrate all of these operators over the unit sphere, you're going to get, well, we saw the formula. So if we integrate these matrices with respect to the Haar measure, you got this formula, which is it's the projection onto the symmetric subspace, a k-fold symmetric subspace, which we saw defined last time, and you divide it by the trace, which is the dimension of this space. I'm sorry, actually, that's not quite right. There's one step here. Let's just do the substitution. So you just plug this in. Put in the binomial coefficient. Right. But we saw that last time, if you integrate over, without this binomial coefficient, you integrate over this k copies of theta, then you get the scale projector, the symmetric subspace, times this binomial coefficient. And the point is that these two cancel, right? These two numbers are the same. And you're left with the projector. And again, we had this thing where we said, well, it's not exactly the identity on the whole space of CD tensor K, but we're only ever going to perform measurements on states that live in the symmetric subspace. So it might as well be the identity. Okay, so basically, for our intents and purposes, it forms a valid POVM. So that's it. That's the algorithm. You perform this POVM. When you do the measurement, you get the name of a vector, ket theta. And now the question is, how good of an estimate is theta of the unknown state psi? Yeah.
I think maybe you mentioned this last time. What does it really mean to take the continuous POVM? Is that something that we can actually perform?
Oh, good question. So yeah, what does it actually mean to perform this measurement?
Yeah.
Right. So basically, any POVM, continuous or not, can be realized as you take your state, your input state, you append some number of ancilla qubits. So qubits initialized in the 0 state. There's some unitary that you can perform on this entire state. So you add your zeros, you do some very complicated quantum computation on the collection of qubits, and then you do a standard basis measurement. And the output of the standard basis measurement will be the name of one of these vectors. So that's how you would actually implement it. Of course, there's a lot of details in what is this unitary transformation and so on, but any POVM can be realized in this way. Okay, thanks. So now we just have to evaluate how good is this estimate? And we're going to measure goodness by looking at the overlap between this state theta and the state psi. So we're going to define a function of theta, which is the measurement outcome, which is the overlap squared between theta and psi. If theta was exactly psi, then this would be equal to 1. If it's very far from psi, then this would be very close to 0. So hopefully it's as close to 1 as possible. And now we want to see if we did this measurement and we obtained theta, what is the average goodness? What is the average value of this function? So does someone remember from last time, what is how do we evaluate this average? Formula for it.
Integral over the outcome space of the raw psi and two psi and ket psi. Right, the theta. Yeah, my
There's something.
and there's f and then f of this. Yes.
Few averages. We're missing one thing, which is actually the input is not psi itself, but k copies of psi, right? That the measurement is performed on k copies. So we just want to figure out what this number is. And we just have to plug in everything we know about these expressions and try to simplify. So let's first plug in our expression for q theta, which was this operator. So we pull out the binomial coefficient. We get this integral. We have our input state. We have these k copies of theta. Input state. And now we also have to plug in our expression for f of theta. But I'm going to rewrite f of theta in a way that makes it more like this. So one thing to notice about this number is you can write it in a nice way or a different way. What would be another way of writing this inner product? Hopefully we should get it to look something like this. Yeah.
Maybe like trace of outer product.
The trace of an outer, yeah. So and another way of writing that trace would be, what would go on either side? Yeah, just so. So these two numbers are the same, right? So let's plug that in here. It looks kind of messy, but we'll be able to simplify in a second. So the next step is we're going to collect our psi's together. Right, really we have k plus 1 copies of psi. We have k copies here and a copy of psi here. We have k plus 1 copies of theta. So we're just going to rearrange this expression. So this binomial coefficient. And I claim that this is equal to k plus 1 copies of psi plus 1 copies of theta plus 1 copies of psi again. So that's our integral. Okay. Now I'm going to, this integral is only over theta, right? So I can pull out this sandwich by psi. So this is k plus d minus 1, choose k. So hopefully this expression should look familiar, right? Like the only difference between this and this is, the difference between k and k plus 1, right? So we can replace this integral with our projector, right? Our formula. So k plus 2 minus 1, choose k. Have the projector of the k plus 1 fold symmetric subspace. Right? This operator acts on k plus 1 copies of a state. And I claim there's a couple of things to notice. What happens to this quantity? By which I mean I'm taking this matrix, this projector, and I'm sandwiching it with k plus 1 copies of psi. Just one, right? Because this lives in the k plus 1 symmetric subspace. So it's just one. So all we have to do is figure out this number divided by this number. So this will be 1 over some binomial coefficient. We just have to replace k plus 1, the k here with k plus 1. So this is going to be k plus d, k plus 1 inverse. Right, and now we just have 2 numbers that we need to bound. All right, so you open up all the binomial coefficients. And it turns out that this is equal to k plus 1 over k plus d. That's something you can verify yourself. So that is to say, we've done all these manipulations. The expected overlap with our true input state psi is going to be equal to this. So if we want to make this greater than 1 minus epsilon, then that tells us how big k needs to be. So the claimed bound of d over epsilon so as long as you have that many copies to play with, you're going to get a good estimate. So we use this symmetric subspace, this Haar measure a bunch of times. One was to first construct the measurement, and then the second was to evaluate how good our tomography procedure is. Any questions about that?
So in this method, the psi doesn't have to be sampled by the Haar random.
This is for any psi. Yeah, so that's the pure state estimation algorithm. It's pretty simple now that we've developed all this mathematical machinery to handle it. Good. Okay, so now I'm going to move on to something called shadow tomography. But first, actually, I need someone to describe this next half hour. What's your name? Asa. Oh, Asa, hey. So we've talked about a couple tomography algorithms. We all see that the number of copies you need is quite large, right? You need something that scales with the dimension, polynomial with the dimension, something at least d over log d. And for any reasonable size quantum system, this is going to be really expensive. So I did some research last night, and I think I found that the world record for performing quantum tomography in the lab is on a state with 10 qubits. And this is sort of stretching the patience and limits of what experimentalists are willing to do. I think it took like a full month to collect all the measurements and sort of collect all the statistics to figure out the state that they were performing. So and no one's going to bother trying doing anything like 20 qubits, which is kind of crazy. So tomography is, I guess, one of the most useful ways for experimentalists to determine what kind of state they have generated in the lab. But what happens when, one day when we build these very large scale quantum computers, and we're generating all sorts of weird quantum states, and you want to find out what kind of quantum state do I have on my quantum computer, right? And it may have 300 qubits or 300,000 qubits. There's no way that tomography will at least in this way, will cut it, be useful. But then you have to ask, like, why actually do we want to perform tomography? I mean, it's useful when you can do it, but at the end of the day, you're sort of getting a very long list of numbers, right? You're getting this really high dimensional vector, but do you actually care about getting this list, right? So. And Again, I'm not a physicist or experimentalist, so I might be putting words in their mouth, but here's what I think is what they're motivated by. So maybe full-blown tomography isn't necessary. Right. What do experimentalists actually care about? Well, they want to measure some, like some physical properties of whatever state they have in the lab. They want to determine what are interesting properties of it. They don't care exactly, what's every single amplitude in the state. Right? Maybe they'll care about properties like what's the magnetization of a certain, collection of atoms that they have, or what's the amount of entanglement. Entropy that's present in your system. What are different correlations that are, what correlations exist between different qubits? Right. What phase of matter are your qubits in? Right. These are the types of questions that you actually are interested in at the end of the day. So that is to say, like, if we realize that we're actually interested in a specific subset of properties of some unknown quantum state, can we get away with using fewer copies of the state than what full-blown tomography would require? And this is the motivation for what's called shadow tomography. Good. Okay, so as an example, it's kind of a trivial example. So let's say you're, there's just one observable you're interested in. Fix an observable, call it A. So remember, what's an observable? It's just some Hermitian matrix that encodes a measurement, and you have weights for all the measurement outcomes. Are you interested in figuring out, for the unknown state psi that you have in your lab, what is the expectation value of this observable? And you want to estimate this to, say, plus or minus epsilon. Right? You're just interested in this one number. So how many copies of this unknown state would you require? The dumb thing to do would be to say, well, let's perform tomography and then compute this expectation value, because you require too many copies of psi. Or you can just get a few copies of psi, do the measurement, and just take an average. Right? So we'll do this using k copies, where k is equal to O of 1 over epsilon, something over epsilon squared. And in this case, it's just going to be the spectral norm of your observable A. So basically the largest eigenvalue squared. And the dimension doesn't show up anywhere. So if the spectral norm of your observable is small, right, maybe it's constant, then you only need a constant number of copies of your state. Right, so that's good. And of course, you know, if you have a large list of observables, then for every single observable, you only need this many. That's fine. But what if you have a huge list of observables? By huge, I mean like an exponentially long list of observables that you're interested in. Let's call them A1 up to A capital T. And the naive way would be to just multiply K times capital T. That's the number of copies you would need. But you can ask, is it possible to do better? If you're somehow using, if you can use the knowledge of the observables that you're interested in. And kind of the amazing thing is that it is possible to save. So that motivates shadow tomography. So shadow tomography is the following picture. You get some number of copies of your unknown state. Think of K as being much smaller than the dimension, right? You have some process. And the output is not going to be an estimate of the state necessarily, but it's going to be some piece of classical data called a shadow. Okay, that hopefully is much more succinct than the state vector. And from this classical shadow, you can compute any of these expectation values that you're originally interested in. So you can compute, say, expectation value of A1 or A2, any one you like. And the hope or the goal is that this the size of the shadow is going to be much, much smaller than the number of observables you're interested in. So you've kind of taken the state a few number of copies, not only the size of the shadow, but the number of copies. You've sort of computed some compressed representation of your state from which you can deduce all the information that you were interested in. So that's what shadow tomography is. So here's what's possible. The first result is due to Scott Aronson in 2015. So let's say you're given T, not just observables, but you're given T projection matrices. So let's call them P1 up to PT. These projection matrices don't have anything to do with each other. So it's not like they sum to identity or anything. It's not a measurement. Instead, we can think of each of these projection matrices as specifying a two-outcome measurement.
The question, you want the size of the shadow to be bounded? I thought we were interested in the number of copies. Okay.
Yeah, also both both, the size of the shadow and also, the number of copies.
It's a common line.
Yeah. Basically, you sort of want to minimize the complexity of any of these steps as much as possible. So it's not the case that, the sum of the p's is as identity. That's not the case. Just think of these as separate, independent observables you're interested in. So you're given these. You're also given many copies of an unknown state. There's an algorithm to compute possible shadow S, which you can estimate the expectation value of all of these projection matrices up to plus or minus epsilon, as long as K is, so it's going to be some power of 1 over epsilon, right? Tilde is hiding like some logarithmic factors, which we won't really care about. There's going to be some dependence on the number of observables, but it's only logarithmic in the number of observables. And there's some mild dependence on the dimension, but it's, again, only logarithmic in the dimension. This is a fantastic number because T and D can be exponentially large in the number of qubits that we have. But the total, this is only a polynomial number of copies of this unknown state. So that's Aronson's shadow tomography algorithm, has this guarantee. And it's kind of mind-boggling because this is any set of projections. You can be interested in any property that you can express in this way of your unknown state. And you can estimate each and every one of them to plus or minus epsilon using only a polynomial number of copies of your state.
Does he provide an algorithm or proves that one must exist?
Oh, he provides the algorithm. Yeah. Yeah, so he gives the algorithm. So this is fantastic. So let's write the pros and cons. There's some drawbacks to this procedure. So the features and estimate exponentially many measurements using polynomial number of copies. And also sort of okay, so I mean that's the main feature, which is quite unexpected. I mean, before this result, it was sort of believed that if you want to get sort of an exponential number of pieces of information about your quantum state, there's nothing you can do better than doing tomography. But this says actually there's a shortcut.
what are the log factors hiding in that? Because there's already like log.
Oh, yeah. Yeah, what is that? I think it's logarithmic in log T and log D. So I think if you were to spell it out, then there'd be like log T, log D factor. But just to make it nice, you just
I have a question actually about this.
Yeah.
I'm just thinking how this doesn't contradict regular tomography. Like, first of all, I'm not sure whether you could, so maybe the problem is you can't really use projection matrices to actually somehow get information about each individual dimension, coordinate. But even if you could, maybe epsilon is the issue, right? Because you would need it to be small at every dimension and then decrease back in that way.
Yeah, exactly. So Dan's question is, maybe this seems too good to be true, because remember that we proved that if you could do tomography too well, then you could transmit these really long messages. Right? But the reason you cannot use this to transmit messages really efficiently is because, let's say you stored your classical message in a quantum state. So let's say you said, here's my quantum state. I'm going to encode a really long function in the amplitude of this quantum state. Right? So this is my quantum state. What if I did shadow tomography on this? And it's not quite what I want, but sort of here's the point. You might try to extract this amplitude, but what's its magnitude? It's exponentially small. Right? So the size of each amplitude of each basis state is 1 over square root 2 to the n. But you're only estimating that up to plus or minus epsilon, which gets swamped out. And so you're actually not going to be able to get all of these bits reliably. So there's no contradiction there.
Unless you use epsilon 1 over less than 1 over square root of the n. You get back.
Exactly. So the drawbacks are, the sample complexity is good, but the time complexity of this algorithm is actually still terrible. And also the shadow is still not any smaller. So, I said that our hope and goal was to, minimize the size of the shadow, have a small number of copies. We could only accomplish with this algorithm to minimize the number of copies. But this processing, this quantum computation that you have to do is still going to take exponential time. And the shadow is also very large. All right, but still, it's very cool. And then people started looking at, well, what if we wanted to have an efficient tomography algorithm? Efficient shadow tomography algorithm. And this is the next result that people came up with. So this is a shadow tomography algorithm due to Huang, Preskill, or Huang, Kuhn, and Preskill in 2019. So this is a tomography procedure that is time efficient. So this is what they prove. So using number of copies that scales as log 1 over delta times b over epsilon squared copies of an unknown state psi generate a shadow S from which so you generate your shadow first, and then you say, I'm interested in certain observables. And your shadow is actually independent of the observable. But there's a catch, so from which you can compute expectation value of any observable M satisfying. There's a technical condition, which is that something known as the shadow norm of this matrix. Okay, and the shadow norm is at most the trace of the square of the matrix. This is at most this capital B. So think of B as some upper limit on the shadow norm of your observable. In some sense, it's sort of saying your observable isn't too complicated, but as long as it's not too complicated, you can estimate this expectation value to plus or minus epsilon with probability at least 1 minus delta over the shadow S. So it's kind of a mouthful, but it's saying that you have your K copies, get your shadow S, and then later, the next day you say, oh, I'm actually interested in some observable M, and provided that the shadow norm of M is not too large, it fits under B, then you have pretty good confidence that your shadow would allow you to estimate this quantity with Python. So how does this compare to Aronson's? And this procedure is doable in polynomial time.
Both the procedure to compute S and the procedure from S to compute some.
Oh, sorry. Good. Okay, that's a subtlety. So which procedure am I talking about? The shadow creation procedure.
Not the matter one.
Not necessarily. That'll depend on your circumstances. And create a shadow takes poly time. Okay, good. So that's an important aspect of this. But first, let's say you had you had many observables, so you had M1 up to MT. Right? Think again T as being something that's like an exponentially long list. Then this gives good guarantees. So basically, we just generate the shadow, and we got to hope that for every single one of these observables, our shadow would provide a good estimate. We're guaranteed that individually, there's a 1 minus delta chance that the shadow you generate is good for each one individually. So the probability that it's going to be good for all of them is going to be at least 1 minus delta t. Right, so let me write that again. Each I, the probability S, over S that estimate is 1 minus delta by the guarantees of the above. So by union bound, the probability over S, you can estimate all of these are going to be at least 1 minus delta times t, the number of measurements, observables. And so this means that really you could have taken you only need k to be O of log t times b over epsilon squared. Right? I'm just saying that delta just has to be small enough so that delta t is still less than. Okay. Which is great. So, you only have a log dependence on the number of measurements. You have 1 over epsilon squared. That's kind of similar to what we had before. And then maybe, the thing you should be wondering about is, what does this be, right? Like, what does it represent? So I said that the trace of m squared has to be at most b. What are matrices that satisfy this? A good example would be if each of these m's is a projection onto a pure state. So if m is equal to, say, projection onto some pure state theta. So how might this be useful in say, an experimental setting? Imagine that you have an exponentially long list of different pure states, right? Theta 1 up to theta t. And someone gives you an unknown state psi, and you want to tell, you sort of want to figure out, is psi close to any of this exponentially long list of pure states? And this shadow estimation procedure will, tomography procedure will allow you to do that. And this is kind of like very, again, very non-intuitive, because like if you didn't know about this procedure, I gave you just a polynomial number of copies of the unknown state psi, how would you be able to determine the overlap with all of these different states? You might take one copy of psi and say, okay, is it theta 1? But if you do that measurement, then that one copy of psi gets collapsed and it disappears. You lose it. And then you get the next copy of psi and you say maybe test against theta 2, and so on. But you're quickly going to run out of your copies of psi if you do this like naive way of doing it. But using this procedure, you can be much more efficient and much more clever and figure out this number for all of the m's. Yeah.
Is there sort of a delta hiding in the errance thing too? Or maybe this is like assumed to succeed of the constant error.
Yeah, constant error.
But otherwise there would be a delta.
Yeah, probably log 1 over delta.
Ernson's thing, does it probably uses the fact that you're given these projection matrices, right? Like, it seems
Yes.
like this one, it just computes a shadow and it'll work for any observable.
Yes. His algorithm actually uses information about the p's.
Okay.
It sort of says, let me take all of these p's and do some number crunching, which takes exponential time, and figure out the best sequence of measurements to perform on my copies of psi.
Okay.
So it's an adaptive thing. This one is completely oblivious to the observables you're interested in. Yeah. the final thing I want to say about this is, okay, I said, well, it's great that creating the shadow takes polynomial time. But if you wanted to, from the shadow, recover this number, it may not be doable in polynomial time. It depends on what your m is. For certain m's, you can compute it efficiently. Other m's, maybe not. The number of copies is small and the shadow creation time is small.
What is the shadow? Like what's the format? Is it matrix? Does it depend on the algorithm?
Good. So I can say this algorithm is actually extremely simple. I'll say this and then we'll take a break. So how does the HKP shadow work? Basically, you get one copy of psi. Like for each copy of psi, you're going to sample a random unitary from a particular set of unitaries. It's in this case, it's called the Clifford group or the Clifford unitaries. If you don't know what it is, it's no matter. It's like a very nice set of unitaries that you can do efficiently. So you sample a random Clifford unitary C. You apply the unitary to that copy of the state. This takes polynomial time. It's very easy to do. And then you just measure in the standard basis. So you measure the standard basis, you're just going to get some bit string B out. And then you're just going to save the choice of Clifford unitary that you sampled and the resulting outcome, C comma B, and that's going to be part of your shadow. And you just do this for every single one of your copies of psi. And together, these pairs, C comma B, are going to be enough to allow you to compute these numbers. And that's it.
So in general, there's no set structure that a shadow needs to take. It's any sort of algorithm that allows us to achieve those goals.
Yeah. Okay, so let's come back at 3:10.
Questions. First, when you say, I'm just curious what a Clifford generated from Clifford gates we talked about in the previous class.
Yeah.
Those like those finite set of gates.
It turns out that any such unitary generated by those has a canonical form of most n squared gates.
Maybe up to some error.
No, exactly.
Oh,
It's a discrete group.
oh, it's error if you want to do any unitary use of those. But
Yeah.
I see. Nice. Yeah, my other question is, what is maybe this is hard why you're this is why you're kind of what really is observable? Like it seems to be, is it always a unitary?
Oh, it's a Hermitian matrix. Any Hermitian matrix is a observable.
So more general than unitary.
Unitary, if it's a Hermitian unitary. So basically, if it's a Hermitian matrix, then you can diagonalize it and think of the projectors that you get representing a projective measurement. And all of the eigenvalues, which are real, are just weights as you assign to the outcome.
You're done. I think you're just doing a Chernow problem, right? You're the one of epsilon's going to estimate.
Yeah.
Where's the spectral norm coming in?
The variance of that, like,
Oh,
Yeah.
I see your wavelengths.
yeah, because A might have like a super huge eigenvalue,
I see,
so the
yeah.
variance.
Makes sense, yeah.
Stop.
Maybe next time. I'll just keep trying.
Yeah. Looks like it's-
Oh, yeah.
Because I think, yeah. Yeah, no, but I think they sometimes refer to it like.
Yeah, I'll figure
Yeah,
out how
they're
many
very-
copies.
An observable. Yes, it assigns a real eigenvector to real eigenvalue, some basis of CD. But then when you do, like, the measurement is, let's say phi, the emission matrix phi.
Yeah.
So it's really taking like an average over phi. And you can actually do that.
One way of doing it is you
We've
can.
only really done like, I've never done projection onto something.
Right. So you would do a measurement as you wanted to do. But then you, once you get the outcome, you say, well, what was the eigenvalue corresponding to that? You know, just off of that. If you do that many times, you take the average of that real number. That will be the expectation value.
I guess what I was confused by was, so an observable, you say it's a Hermitian matrix, that's just like a way to compact
I
it.
think it's hard for
Doesn't mean that that
it's
is
harder to write
a
on
single like thing that you could measure once.
It's just collecting information of some experiment you want to do into one matrix.
The general observable you can do is measure like different eigen.
Here, then like you break stuff.
Yeah, I can't erase things, so my notes are covered with like
Even they look aesthetic though.
Okay. No worries. Actually, around that time, there might be a very exciting question.
We change the order, make the boring ones at the end.
Is the crypto submission?
Oh,
Goodness.
30 minutes early.
Wow. Nice. Yeah. We just ran out of steam. We're like, okay. we'll just submit it.
We were page over them. Very happening.
I missed the party.
One or two.
Okay, so let's get into. I was really looking forward to this because, like I was mentioning, the questions that you submitted were all really awesome, and we're not going to be able to answer all of them, but I sort of curated some of the ones that I thought would be good for discussion. But for the ones that aren't discussed here, we'll also have answers to them, and we'll post them online. So thank you very much for submitting them. So let's see what people are interested in. Okay, so first question. When performing tomography, especially given that we have this no quantum Xerox machine, also known as the no cloning theorem, tomography requires many identical copies of the state, right? Like I always write psi tensor k. But how is it possible to get identical copies of the state? And, or how do we guarantee this? So the answer is, in general, we cannot guarantee that we have many, like in the most general setting, we cannot guarantee that we have many copies of the state. It's just part of the assumption of the tomography algorithm, right? So from the point of view of like experimentalist, you sort of assume that you have some box that you can press a button, and every time you press the button, the same state will come out, right? So maybe it's some physical process that you generate some cool state, and you're like, well, what state do I have? You just run the process over and over again, get many copies, and run tomography on that. Sort of in the most general case, if you're only given one copy of an unknown state, and that's your only chance to get it, you're sort of out of luck. Like that is a very precious copy.
I mean, we can check equality, right? Or like, is that not known? to be done efficiently. I have two states. I want to know if they're like the same state.
Uh-huh.
Can I do that?
You can, but it doesn't work perfectly. So there's something known as a swap test. So if you're given two pure states, psi1 and psi2, and you tell if they're the same, then you can, there's a very easy quantum circuit that it's called the swap test. If they are the same, the circuit will tell you yes with certainty. If they're different or orthogonal, there's still a half chance that it will confuse and say, oh, they actually are the same. And that's the best you can do. Great question. All right, so another question is, what specifically is involved with the complexity of a quantum state? For instance, do certain gates add more complexity to the states? And if so, what analogs do they have to classical complexity? So remember that the way we defined the complexity of a quantum state was, we said, well, you first have to fix what gates you're talking about, right? You have to fix some universal set of quantum gates. Once you fix that, then you say, what's the minimum number of gates do I need to manufacture the state from scratch? Up to epsilon error. That's the definition of complexity. And it depends on your gate set, of course. But the nice thing about this notion is that it's fairly robust to your choice of gates. So if you had one notion of complexity, like C1 with respect to gate set 1, and then another measure of complexity with respect to another gate set 2, these cannot be too far from each other, provided that you're using a universal set of gates, right? These will be, it won't be the case that one is exponential and one is polynomial. They'll always be polynomially related to each other. And it's very similar to the case in classical complexity theory, where when we're analyzing the complexity of algorithms, we say an algorithm is n squared or polynomial or exponential. We don't really specify exactly what type of computer, or is it a Turing machine? Is it a circuit? Is it a RAM machine? Like all of these are polynomially related to each other. So for that reason, we kind of don't care so much about exactly what gates you're using. So hopefully, I forget who asked this question, but hopefully to your satisfaction. Another question about complexity. So if you're given this challenge of actually building a quantum computer, which is pretty challenging, we're not able to do it yet, at least on a large scale. Are these notions of complexity like transferable, right? We're sort of like using our notions of complexity from classical computer science and adapting it to the quantum setting, but is it like, does this make sense, right? So, for example, linear time on a classical computer means it's super easy, right? You don't even have to think about it. But actually, if you want to run a linear time quantum algorithm, like we don't know how to do this on any reasonable number of qubits. Right? This is just too difficult. So I guess the answer is, or one answer is, it really depends on what you care about. Like if you're an experimentalist who's actually trying to create a quantum computer, then these notions of complexity where you're measuring the minimum number of gates and so on, it's irrelevant or uninteresting, right? Like you're just focused on, like you want to build your qubits or your quantum computer. But if you're interested in like the intrinsic difficulty of some computational problem, you sort of want to separate that from the difficulty of engineering a quantum computer, right? And you sort of just want to sort of abstract away and say, well, if I have some notion of an elementary operation that I could do at unit cost, right? Maybe it's applying a quantum gate or something, and I just take that as my unit operation, then it sort of makes sense to sort of just measure complexity with respect to that, right? And not worry about how exactly my qubits are implemented and so on. I think that's all I have to say for that. Is the randomness when sampling from a hard distribution classical or quantum randomness? Is there a possibility of using quantum randomness to generate or approximate our random states? So this is a good question, but in some sense, it's not very precise because, and I think partially that's my fault. It's not clear what classical versus quantum randomness means. In the previous lecture, remember I described these 4 scenarios, right? One where I'm sampling a random classical bit string and then putting that in a box versus sampling a random quantum state and putting that in a box. So the random bit string, I was calling that classical randomness. Okay? And whereas if I'm picking a hard random state and generating the quantum state, putting that in a box, it's quantum randomness in some sense. But these are very vague terms that sort of it's not a well-defined. It was more of an intuitive notion to sort of explain the difference between these scenarios. And yeah, so basically hard random states, you can say it's not classical randomness because it's not a classical bit string. So still confused about the usefulness of the hard distribution. We spent some time talking about it. What are applications of this distribution? For instance, if a state is hard random, are there cryptography applications that can arise from the state having high complexity? There's dots because there's more to this question, but I kind of curated the sentence. And there's another question which is related is, how does the hard measure connect to the dynamics of black holes? Okay, so it's kind of a, so let me talk about the first thing. So what are applications of the hard distribution? And we already kind of, hopefully you saw an answer today, we talked about this pure state tomography algorithm that the continuous POVM is defined with respect to the hard distribution. So that's one application. Other applications that we'll talk about in this class there's going to be a bunch. Okay, so definitely one of them is going to be crypto applications. So just to give you a sneak preview, in this setting, we're going to talk about something called pseudo-random quantum states. So these are states that you can generate efficiently on a quantum computer. But if you handed the state to someone on the street, they will not be able to tell the difference between this state and a state that was picked from the hard distribution. Now, of course, because you actually generated the state efficiently, there's no way that it's going to be hard random because it's not high complexity. But the assumption here is that it actually mimics the hard distribution. So these are called pseudo-random states. And what we're beginning to learn is that these types of states can actually be very useful for cryptography. You can use these states to do things like encryption or to do secure multi-party computation. And you're really relying on the fact that it mimics the hard distribution. So that's one application. Another application of the hard measure is in something called quantum supremacy. So what does this refer to? So in 2019, Google had this really landmark experiment, maybe you've heard about it in the news, They had a 49 qubit quantum computer. They took it, they chose a random quantum circuit. They ran it on their machine. So they sampled a random circuit. It's 49 qubits wide. The circuit consists of 1 and 2 qubit gates at depth maybe 20 or something like that. The circuit of depth 20 was kind of the limits of what their machine could handle. And at the end, they just, you get some quantum state out. And they just measure this quantum state in the standard basis. So you measure, you get some bit string out. That's 29 bits long. And they just did this over and over and over and over again. And you just collect, millions of these bit strings. And what they verified is using some supercomputing time, is that it is very likely that the bit strings they obtained came from the distribution of if you actually ran this circuit on an ideal quantum computer and measured it in the standard basis. So they're kind of checking that the state that they generated on their machine really looks like the state C times the all zero string. Okay. And the assumption is that this tells you a couple of things. One is that this machine is working as intended, which is great. Okay, it's a lot of qubits. B, there are complexity theory arguments for why no classical computer can sample from the same distribution efficiently. What that tells you is that whatever this machine is doing, it's sampling from a hard distribution that cannot, it's not classically simulable, right? So that's why they call it quantum supremacy. Where the hard distribution comes in is that they're assuming in these complexity theory arguments that this state, let's call it psi, mimics a hard distributed state. Like if you measure all of the you sort of look at the amplitudes of the state, it sort of looks like it came from the hard distribution. Right? There's a distinctive profile to these amplitudes. Right? If you were sort of like to plot out, you look at all these amplitudes and sort them from largest to smallest, it's not totally uniform. There's actually like a very distinctive shape. And this is just a cartoon, that's not what it looks like, but there's some shape to it. And it tells you that really this state is highly complicated and highly entangled. Looks like a hard random state. So that's another element.
What if it's a pseudo-random and it's not? What if it just looks like a hard state, but it's not really? Like seriously, how do they know that it came? They basically measured that it came from. I guess my question is the first thing you said. How did they figure it out?
How do they verify?
How did they verify that it came from this distribution that is not sampleable?
Right. So it's they collected like millions of samples, but it's not enough to reconstruct the distribution. Like every single sample will be a distinct bit string. So you say, well, what's the point? The point is that they checked in the ideal distribution, what is the probability of each of the bit strings they obtained. And it turns out that the probability of each string is going to be higher than the median, like significantly higher than the median probability. So like basically they obtained heavy hitters that they expected. And the complexity assumption is that this cannot be performable by a classical randomized Turing machine in polynomial time.
Or else what?
Polynomial hierarchy collapses. Yeah. The universe as we know it explodes and we continue on with our lives actually.
Information being processed in this crypto application, is it like classical information or like actual quantum states being encrypted?
And here, this is in a world where everyone has a quantum computer and we're transmitting quantum states back and forth. The good guys are using quantum states, the bad guys are also using quantum states. Necessary.
what is this distribution over? Like you're starting with a known state of all zeros, and you have a fixed quantum circuit. Isn't the expectation that the output will always be same with regards to without some errors? Why is this a distribution? Isn't the output always psi?
Oh, good. What distribution am I talking? I'm telling you, you take psi, it's a pure state, it's fixed, but then you measure it in a standard basis, and you get a classical bit string out with probability that's B. This is the probability of obtaining bit string B. So there's going to be some distribution. Okay. Okay. So other uses of the R measure. So we're not just, so here we've talked about R random states, but another type of R randomness that we'll talk about are R random unitaries. Okay. So these are unitaries that are, just think of it as like a uniformly random unitary. Okay. These are very, very important in quantum information theory for all sorts of reasons. One reason that they're useful is that in a lot of like information processing tasks, like if you want to compress quantum states or you want to make them resilient to noise and things like that, it turns out these protocols use R random unitaries. And one reason why they're very useful is because if you apply a R random unitary to a quantum system, you completely scramble it. And you'd be like, why is that useful? But it turns out that this is a very useful thing. Okay. So that's another application. Just sort of give you some intuition. If you pick a R random unitary and you apply it to a fixed state, like the all zero state, can anyone guess what's the distribution of this resulting state? R random. Okay. So it's sort of like a generalization of R random states, R random unitaries. And now this connects to the answer to the second question. And so here's some like background. So for over like basically over a century, one of the biggest open questions in physics is how do you reconcile general relativity and quantum mechanics? Okay. So these are two of the most successful theories in all of science, right? We've never found a counterexample to any of these theories, right? They describe to fantastic accuracy, like the motion of galaxies, all the way down to how atoms and molecules and everything behave. But these two theories are not compatible with each other. At least we haven't figured out how to make them compatible. So that's still an open question. What people realized since like, so Stephen Hawking, everyone knows Stephen Hawking, one of his great contributions to physics is to realize that black holes, which are sort of these extreme objects in relativity, right? You have the extreme gravitational forces. They're actually, you can actually view them as quantum mechanical objects. So and by thinking in this way, this led him to come up with this notion of Hawking radiation. Okay. Black holes can actually emit radiation, which was not expected. And this is a purely quantum mechanical effect. So today, people think that in order to like reconcile these two theories, the place to start is to think about black holes, right? That's where all the extreme stuff in both these theories is coming to play. It's sort of still an open question, really, how do you reconcile the two? And there's currently people have kind of distilled it down to a very simple paradox, something called the firewall paradox. Something we'll talk about later. And in the firewall paradox, this is where there's three different postulates. Two of them come from quantum field theory and one of them comes from general relativity, and they're just logically inconsistent. You sort of arrive at a contradiction, and people don't know how to resolve this yet. But people have tried to figure out how to resolve it. And sort of today, the current understanding is that however we resolve it, if we're thinking of black holes as like quantum mechanical objects, a very useful model of thinking about them is to treat them as Haar random unitaries. Right, so if we sort of think that if you have a black hole and you jump into a black hole, it's not a very pretty thing. You get spaghettified, right? You jump in and then you sort of get smeared all around, right? It's not a pretty ending. And quantum mechanically, the way to sort of model that is to use Haar random matrices. And it sounds kind of like superficial, but actually by modeling it this way, they reproduce a lot of predictions that actually come from the gravity side. So this is something that they've gotten really excited about. They say, on one hand, you just do a purely quantum mechanical calculation about black holes. And this matches exactly with something on the other hand where you use a purely gravitational calculation. Right? So there are hints of some connections there that they're trying to figure it out. So it comes from that. Okay, so that's sort of like a preview of some of the things that we'll talk about. Okay. This is a great question. How do we actually send a qubit? It's easy to imagine sending a classical bit as, you send like an electrical signal or something. But what does it mean to send a qubit? And I assume there are better ways than packing a qubit in a box and having FedEx deliver your qubit. And that's true. So the way to sort of think about this question is, with bits, a bit is sort of separate from its physical embodiment, right? A bit is just a unit of information. You can represent bits in many ways. You can have electrical charge, you can have a light bulb that's on or off, so on. But how you transmit that bit depends on its physical embodiment. And that's the exact same thing with a qubit. There's many ways to embody a qubit. You can have a photon store the state of a qubit, right? A photon, you can say, store a qubit in its polarization, right? Light is polarized horizontally or vertically. Can represent a qubit. And so you can transmit that very easily. You just let the photon fly and do its thing, right? You just send it down fiber optic cable and it gets from point A to point B. Or you can also represent a qubit as, for example, the state of a macroscopic object like a cat, right? It can be alive or dead, right? That's a qubit. And indeed, in that case, you can have FedEx deliver your qubit by delivering the cat in the box. So it really depends on your physical implementation. Okay, so those are the questions that I thought would be good to share. There, and I'll write answers to all the other questions and post them soon. So that's it for today.
And that's this Q&A. It's great.
It is nice.
No, this is great. Yeah.
It's really good. Exciting.
Thanks for the questions.
I have one more question. So I
yes.
someone at the beginning asked like how do we actually perform like continuous measurement? I'm still a little confused. So like even if we add a lot of bits, if the continuous seems to denote there are infinite kind of measurement results. So how can we actually through like standard basis measurements get the result, or like is it too simple?
Yeah. So Yulan's question is how do we how do you actually perform a continuous measurement? Because like the output is like could be infinite precision, right? So there's two answers to that. One is, of course, you never implement it exactly. You do some finite discretization. Okay, so then it's just really just a finite POVM, which is easy to imagine that you can do it. But it turns out that another way of thinking about it is, and this is like a theorem that I don't know the proof to, that every continuous POVM can be represented as you sample classically a finite POVM on a classical computer first, and then you perform that finite POVM on your quantum computer. So that's equivalent.
That's very nice.
Yeah, but actually I would like to know the proof, but yeah, turns out to be true.
That's it.
Wait, are we like done?
Yeah, you guys
Oh,
free to go.
okay. Thank you.